If you would recall, yesterday we wanted to look at these two functions, and we wanted to do derivative stuff and integral stuff. So we had those two things. Those are the two things that we did. And then as a bonus question, find a formula for g of y and h of x. G of y is pretty straightforward. H of x is a little bit more complicated. It is 1 degree more difficult. Yesterday, because I can't shut up, we only got through approximating the tangent lines or the slopes of because I actually didn't want the whole tangent line. And so we just did rise over run with the information that we have. So today we want to look at finding the area under a curve and above an interval. So let's take a look at the integral from 0 to 6 of g of y dy. We can find over and under estimates by assuming that the function is constant on each interval. In the case of g of y, we're going to assume that z is constant on each 2-unit interval, because this is the simplest thing that we can do. You can just say, well, I'm going to use a value of z of 14 for that first 2-unit interval. We're just going to flatten out the function. I can't multiply and just take one z value for the whole 6-unit interval. So I'm going to have to drop back down to adding. And I'm going to use one z value for each 2-unit interval and just do that 3 times. So for part 2, we're going to assume z is constant on each subinterval of 2 units. We're going to assume z is constant on each 2-unit subinterval. On that first subinterval, an overestimate for the value of z will be 14, and an underestimate for the value of z will be 10. So the most we could get from that interval, on that interval, is 14 times 2 for an area of 28. So our overestimate is going to be 14 times 2, 28. So we're going to use 14 for our overestimate, and then we'll use 10 for our underestimate. The function g of y does something between 0 and 2. It starts at 14 and ends at 10. We don't know what's going on in the middle, so we're just going to use 14 for that whole 2-unit interval. And the d should not be multiplied without necessity. So we're just going to do our necessary multiplications. What we're doing is we're imagining what the graph looks like. We're imagining the graph as a bunch of steps. How many do I have? 14, 10, 6, and 2. Started too low. Boy. So for our overestimate, whatever the function is actually doing, we just have these points, 0, 14, 2, 10, 4, 6, and 6, 2. For an overestimate on each of those 2-unit intervals, we're going to pick the larger value. So I'm going to start with, on my overestimate, we're going to use 14 for that 2-unit interval. And so that is going to be the area under the curve. And then for the next interval, we'll have 10. I'll use that for the area under the curve. And at this point, we just use the only area formula we need, length times width. And then for this third interval, I'll use 6 for the height. Since we use 2 the whole time, we can factor the 2 out and get a clear picture of what we're doing. I'm taking the width and multiplying by all the left endpoints. Since this function is decreasing, the left endpoints are going to overestimate. For the underestimates, we're going to use the smaller value. G of y is between 10 and 14, so I'm just going to use 10 the whole time. And so here's what our underestimate is going to look like. Good question. And then we just add those up. Those are some numbers. This is just a calculation. You may or may not remember how this calculation works in Calc 1 and Calc 2, but that's how the calculation works. More importantly, is the assumption that we used to get to this calculation and where we could take this from here. The assumption was that g of y was constant. That's why we're drawing a flat. The reason that we made that assumption is that we want to use multiplication. We assume that g is constant on each interval so that we can use multiplication. That's all the integration is going to be, multiplication, but one of the factors is variable. If we had a nice constant 14, then we would get to multiply the whole time. But unfortunately, our function is like, oh no, I'm going to change values. But we assume that g of y is constant. So that we can use multiplication. The question said calculate a definite interval, but the question said calculate area. And so we used the only area that we need, length times width. Then we looked at our problem and said, oh, we don't have one length. We've got a bunch of different lengths. But it was, we have this information, just 4 values. So we just assumed it was constant on each 2-unit subinterval. If we had more information, we would assume that the function is constant on each, say, 1-unit subinterval, or a half-unit subinterval, or a 10th unit subinterval, or 1/100th of a unit subinterval. But it all comes down to assuming that the function is constant, so we get to use multiplication. Area is length times width. So all integration is multiplication. The calculus part comes in, and infinity walks into the picture when I don't have a discrete set of values for my function, but those values are changing continuously. Questions? Whatever application problems you did for integration in Calc 2, it all came down to this. You just want to multiply. Area is equal to length times width. Volume is cross-sectional area multiplied by height. Mass is your variable density multiplied by your volume. Work is your variable force multiplied by the distance. We had to do integration because things were changing continuously. Any questions? Of course not, because we did Calc 1 and Calc 2. We know what the thinking is. We want to do a similar thing for h of x. We can just kind of copy what we did here, because it's the same kind of thinking. Anybody come up with functions for g of y and h of x? You should save that, because I'm going to put it on the quiz. Here's what we want to do now. Here's what we want to do. I want to write z as a function of x and y. Each input is going to be a pair, x and y. So you make this function go. To get an output, you need an x and a y. So the inputs are ordered pairs. the inputs are ordered pairs. Then the output is just one value. We're taking inputs as ordered pairs and outputs as real numbers. Hashtag used to be the word for numbers, or the abbreviation for numbers. So I'm not saying the output, there's a real hashtag. But it sounds like you're complaining about something, like hashtag is a bad thing. So, oh man, this guy's being a real hashtag over here. I think it works. What would it be when you complain about someone being a real hashtag? I know. It's like from Clueless. I think it was from Clueless. When she said, stop trying to make fetch happen. I think the similar complaint in 2022 would be like, oh, you're being a real hashtag. Don't leave your email open when you're trying to record stuff. Are you done? Okay, I think it's done. So what were we talking about? We're going to build a function of two variables. All we're doing is instead of one real number input, one real number outputs, ordered pair input, two real numbers inputs, one real number outputs. Oh, I'm not going to be able to make a table that just goes one direction. I'm going to have, let's say, I'll put the x's in columns and the y's in rows. So we're going to build a table that has rows and columns. So I'm going to put x's in columns. I don't know what I just said like 30 seconds ago, but it's going to be x's in columns now. And I'll put the y's in rows. And let's see why we have to do this. Because the inputs are ordered pairs. I need an x and a y to get an output. Here, asking what's f of 0 makes no sense. This function is like, oh, nah, I don't know what you're talking about. I'll need 2. But if you're like, oh, f of 0, 0, the function can say, ah, yes, that is 14. So this point right here says f of 0, 0 is equal to 14. Someone is scheduling meetings. That must be what it is. I think we've gone to the point where emails don't need to send an alert. I don't want things to bing when I have an email. I'll get to email when I get to it. I think we've advanced to the point where the only thing that should alert us is a text, which is the best phone call. I do that to my mom. It's kind of mean, I guess. But I had to teach my mom how to text. Because it used to be that she'd call, and if I didn't get to my cell phone, then she'd call on my home phone, and she'd leave messages everywhere. So we got her a smartphone, and now she's all about texting. It's awesome. Like, well, Mom, you realize you can't hear me very well when you're on the phone, so now you can just text. And it's way better. And then she pulled the Uno reverse card on me a while ago. I like tried calling, and I got a text back, said, just text me. I go, oh, damn, Mom. All right. So wait, what were my values of x or h of x? 14, 16, 20, 26. Now you can see each input is an ordered pair. We're gonna have to fill out some more information. Anyone know what goes here? Look for the pattern before I write it. Just think about what it is. 18. And here. Nice. We had to come up with the rest of the information for me to see what I'm doing. So to say, ask a question like, what is f of 2? That doesn't make any sense. But I could ask the question, what is f of 2, 9? If, oops, I can't ask 2, 9. What did I try to ask here? 9, 2. Yeah, thank you. See, the stuff writes itself. I told you this was going to be the easiest of the calculus classes. 9, 2 is going to be 22. So to evaluate these functions, we need an ordered pair for an input. What if I asked you to solve the equation? What if I said solve f of xy is equal to 12? What are the solutions? They're going to have to be an ordered pair because the output is a 12. The inputs for this function are ordered pairs. So if the output is a 12, what inputs do we have? What are our solutions? Looks like we have one. There's a 12 here. There's a 12 here. Looks like we have two solutions that we can see. So it looks like one of the solutions is 3, 2. And the other solution is 6, 4. Note that in this regard, the stuff that we're doing with these new functions of two variables is the same stuff that we did with functions of one variable. Given an input, evaluate to find an output. Given an output, solve to find the input. Same stuff, just more input. Any questions? How's everybody okay? Is anybody weirded out that I put the X's going this way? Like that's the first thing you have to read in the columns? Because I am. Oh well. I had to go one way, right? So one more thing before I ask a question. Here's what we want to notice. When we have a function of one variable, when we have a function of one variable, that will represent a one-dimensional curve in two-dimensional space. That's not new. You already knew that. You just might not have heard it phrased that way before. When we have a function of one variable, When you think about the graph of a function, we're imagining a one-dimensional curve in two-dimensional space. We have input x, output y. Our curve is one-dimensional. And we are in two-dimensional space. Our abbreviation for two-dimensional space is going to be this R. This double barred R represents the real numbers, but I'm dealing with two real numbers, an X and a Y, so I'm going to call this R2. We're going to write the 2 as a superscript, but we're going to say R2. Which means that droid from Star Wars was improperly named, because that is a one-dimensional character at best. The curve is one-dimensional because if you're on the curve, you can only go left or right. It takes you up and down on this roller coaster, but there's only left and right. You're locked onto a one-dimensional object. We're in two-dimensional space because we have one dimension for the inputs and one dimension for the outputs. Agreed? So when we have a function of one variable, we're dealing with a one-dimensional curve in two-dimensional space. So if we're dealing with a function of two variables, think about the inputs, think about the output, and think about what that means geometrically. How do we take our previous statement? Function of one variable, y to the f of x is a one-dimensional curve in two-dimensional space. How do we adapt that description to a function of two variables? Let's take a minute and think about that. Oh, right, I did not have this queued up. Commercials, hang on. Unskippable commercial. Oh, come on. YouTube, you're encouraging me to steal stuff. There we go. Now, upgrade that statement. What f of x is a one-dimensional curve in two-dimensional space. What is f of x y going to be? Sometimes think about it. I'll probably make it stop. This is the 10-hour. Oh, this is only a 15-minute version. So upgrade that statement. What are we picturing? Our inputs are no longer just a number line above which we're putting a height. Our inputs come from an entire plane, the XY plane. And above every point on the XY plane, I'm putting some height, the output. We're graphing it in the same way. Like I said, nothing changes in this class. We just upgrade all of our old shit. Our inputs are no longer just one real number. Our inputs are ordered pairs that come from a plane, and our output is a height above the plane. So what are we going to be looking at when we have a function of two variables? Any ideas? Let's see. So our inputs imagine that this is the floor, and our outputs are going to be heights above this floor. That's where we put our z-axis. Forgot my color coding already. So we'll have an input down here in the floor, and our output will be a height above the floor. What space are we in? We have two inputs and one output. How many dimensions do we need? 3. I need to be working in 3-dimensional space. And for every input on the floor, I have an output some height above that floor. So what is my collection of outputs going to look like? How many dimensions is it going to be? Just the outputs. Remember, our function of one variable was a one-dimensional curve with two-dimensional space. Now we've narrowed it down. We know we're working in 3-dimensional space. What is our set of outputs going to form? It's not going to be one-dimensional. How big is it going to be? And what we're going to call it a surface. And we're going to use our fancy terminology, R3. Spell 3 correctly. So our function of two variables will make a two-dimensional surface in R3. So imagine the floor is the XY plane. It's curved a little bit up, I think, but that's okay. It's flat enough. We're also standing on the earth. It's not exactly flat, but we're looking at a place That's such a small section of the Earth, it's flat enough. If you look closely, everything is constant. If you look close enough, everything is flat. So imagine I'm just going to put a height of 3 feet above every point on this floor. Then I'm going to make, and I'm going to build a sheet of paper that just is 3 feet above the floor everywhere. That's going to be our surface. That'll be a very simple function. F of x, y equals 3, because every point above the floor has a height, we have an output of 3 feet. Then if I start mucking with what the function says, I can get that surface to be all wobbly. If I make the x's increase linearly in one direction, in the x direction, oh, I should pick y because of the one I did. Make it match with what you saw, whether you saw it or not. In the y direction, I can have all the z values increase, and I can make it linear in the y direction. Then I can make the x's some sinusoidal function, make it all wobbly going this way. A function of 2 variables will produce a 2-dimensional surface in R3. Oh gosh, oh, this is big. So here's the question for today. Here's the question for the weekend. This one's just going to hang there all throughout the weekend. We have our 2 calculus questions. The derivative question, the integral question. You know, calculus is involves these 2 big questions, the derivative question, the integral question. What is the derivative question now? What is the integral question now? I'm going to pause the video here so that I can take roll. That's going to do it for today. That's going to do it for this week on the video. Everybody have a good weekend. Think about these 2 questions, and I'll see y'all on Monday.